Hi class, welcome to Unit 4, Lesson 1, where we'll look at waves in 2 dimensions. So today's learning goal is you'll be able to demonstrate the understanding of transmission, reflection, and refraction, and investigate universal wave equation. You'll know that you've achieved this if you can describe in detail transmission, reflection, refraction, and partial reflection, partial refraction. Identify the universal wave equation and waves traveling from deep to shallow water. Solve problems related to waves in 2 dimensions. And apply this thinking and learning to daily life problems. There are 2 types of waves we're going to be looking at. The first one is transverse wave. And this is a periodic disturbance where particles in the medium oscillate at right angles to the direction in which the wave travels. And a big example of these are water waves. And by that, what I mean by that is particles, when it's still, it's straight, right? The particle here moves up to this position. This particle moves down to this position. And when it waves up, it'll move back, it'll move up to here. So we have this up and down motion, and the wave is moving this way, right? Or it could be the other way too, left to the right, but in any case, right angle. And as for longitudinal waves, these are disturbance vibration parallel to the motion of the wave. So we have vibrations and compressions causing waves to appear in this slinky type thing example. And this is a good example of this is in sound. It's a longitudinal wave. So let's talk about movement. A wave originating from a point source is circular, whereas a wave originating from a linear source is straight. As a wave moves away from its constant frequency source, the spacing between successive crests or successive troughs, the wavelength, remains the same, provided that the speed of the wave isn't changing. And so that we have the wavefront is the leading edge of a continuous crest or trough. So that's this part as opposed to this part, not this part, but just to differentiate, as well as this blue front shield looking part. And the wave ray is a straight line drawn perpendicular to a wave front, indicating the direction of transmission. So it's telling you which way the wave is actually moving. Next, let's talk about the universal wave equation. So when the speed of a wave decreases, as it does in shallow water, for example, the wavelength decreases, since the wavelength is directly proportional to speed. And so when the frequency of a source is increased, the distance between successive crests becomes smaller, since wavelength is inversely proportional to frequency. So we have lambda, wavelength, is inversely proportional to f for frequency. Both proportionalities are consequences of this universal wave equation. V equals f lambda, where speed is v, frequency is f, and lambda is wavelength. This equation holds for all types of wavelengths, 1-dimensional, 2-dimensional, and 3-dimensional. So that's why it's called the universal wave equation. So let's consider a ripple tank where we have a wave traveling in deep water and it has a speed of v1 equals f1 lambda 1. Similarly, v2 equals f2 lambda 2 for the wave traveling in shallow water. So in this ripple tank, to perform an experiment with waves in water under controlled conditions, the frequency of a water wave is determined by the wave generator and does not change when the speed changes. So thus we can say f1 equals f2, and if we divide the first equation by the second equation, it looks like this. If we do left side divided by the left side and right side divided by the right side. So the V1s are going to be on top, so we do V1 divided by V2 is equal to F1 lambda 1 divided by F2 lambda 2. And since we said the machine determines the frequency, it doesn't change. We can treat them the same, so they end up canceling each other out. And so we're left with V1 over V2 is the same as lambda 1 over lambda 2. So we have this type of equivalent ratio. We've kind of seen something like this before with the 1s matching and the 2s matching. And so this is just saying that essentially the ratio of this speed and this wavelength is the same ratio or value as these two put together. And they both come to the same value, which is F1 or F2, which are the same here. And so just how to read this, picture these are the waves like above the water, and the darker ones are the troughs underneath, like this. So these ones are the crests and the troughs. So we can tackle a problem now. So a water wave has a wavelength of 2 centimeters in the deep section of a tank, and at 1.5 in the shallow. If the speed of the wave in the shallow water is 12 centimeters a second, what is its speed in deep water? So that means we have V2 here, lambda 1, and lambda 2, shallow. Okay, so now our values, lambda 1, lambda 2, V2, and we want to know the speed in the deep water, which is V1. So we take this ratio because in this tank, we know that this ratio holds true because the frequencies are the same. And so we can solve for V1, bring V2 to this side, and then we substitute our values. Everything is given in centimeters, and the speed is centimeters a second. So we end up with centimeters a second, so that's okay. Right? Centimeters cancel out, we have centimeters a second. And so we're left with the speed of the wave in the deep water, which is V1, is 16 centimeters a second. So for reflection, a ray of light, the incident ray, travels in a medium. When it encounters a boundary with a second medium, part of the incident ray is reflected back into the first medium. This means it is directed backward into the first medium. So the law of reflection, we have, so when we have a reflection like this, we're going to have a normal, which is a line that's perpendicular to the surface, and it is at the point, it starts at the point where the incident ray strikes the surface. So it's at this point, it goes straight up, perpendicular. And then we get an angle here, and the theta here. And so it makes an angle of incidence, and it makes a theta r, which is an angle of reflection. And the law of reflection is that the angle of theta r is equal to angle I, theta I. So the angle of reflection is equal to angle of incidence. And so we have an example of when a straight wave front meets a straight barrier head on, it's reflected back right along its original path. So right against the barrier, comes right back perfectly reflected. However, when a wave encounters a straight barrier obliquely, kind of diagonally, rather than head-on, the angle of incidence still equals the angle of reflection. So to read this, remember our wave ray is showing the direction of the waves. So incident, this is for the incident wavefront. So these are multiple crests, troughs, multiple waves, and they're headed this way. And then this is our barrier, and it hits it kind of on this angle. And then it comes back with these dotted lines that are going like that direction. And so we still have our reflection angle equal to that of theta I here, incidence angle, using the solid blue versus the dotted blue waves. And so they still equal each other even obliquely. Next we have refraction, which is a phenomenon that is the bending effect on a wave's direction that occurs when the wave enters a different medium at an angle. And we have going from higher speed, deep water, and to lower speed, shallow water. Again, our instant wave ray is before the incidence before, and this ray tells us which way these waves are going, traveling this way. And then we have a oblique boundary. And so when the water waves travel obliquely into a slower medium, the wave rate bends toward the normal. And so we have this normal, right? Perpendicular to the point of contact. Here's the point of contact directly up. And instead of going like this, it's slightly down and coming toward this normal more. And so if the new medium is a faster one, the wave rate is going to bend away from the normal. So if we go the other way from lower speed shallow water to higher speed deep water, we're coming in with this incident wave ray, and instead of continuing kind of like that, a little bit straighter, it bends away from this normal. Notice how it's bending away from that normal. Instead of here, it bends this way. So that's for when you're moving into a new faster medium, and before is for a slower medium. So just to review again, for a normal, in refraction, it's a straight line drawn perpendicular to the barrier struck by a wave. So we have this, and angle of refraction is theta r, and the angle between the normal and the refracted ray, so right here, or it's between the refracted wave front and the boundary if we have a front. And so we're not going to go over the math, but from this diagram we can derive a useful formula, which is sine theta of incidence over sine theta refraction, and we have lambda 1 over lambda 2 is equal to it. We'll use that in the next few slides. So for light, when light passes from one medium to another, it is refracted because the speed of light is different in two media. So just like when we had a wave coming from a slower medium or faster medium, and then it came out into the opposite, it would refract a little bit from the normal, right? And so same thing goes with light, and so the index of refraction n can be represented with the speed of light in a vacuum as well over the speed of light in a medium. And so with this phenomenon, the frequency is going to stay the same as the wave travels from one medium to another, and the ratio of indices of refraction of the two media can be expressed as various ratios. So we can say that n2 of a certain medium 2 and n of n1 expressing this ratio, and we can substitute if we take our ratio that we saw before. We saw this one. And so since the V1 is equal here, since this equals n, we can rearrange them, and we can get V equals C over n. And so we do that for each medium, C over n1 divided by C over n2, and the C's cancel when you flip and multiply by the inverse, and we get n2 over n1 ratio. Notice we have them flipped. Instead of 1, 2 here, 2, 1 on this side. So the formula we didn't go through the math for, if we take that, this formula, and we see lambda 1 over lambda 2, and we found in this slide that we had lambda 2 over lambda 1 is equal to n2 over n1. If we substitute that, then we manage to get Snell's law of refraction, which looks like this, where theta 1 is the angle of incidence. So we've seen it so far with theta I, 30 degrees here, and theta 2 in this case is our angle of refraction that we've been seeing. And so here's an example from a medium of air into glass, the refraction that takes place. And so since we had all those ratios, we had all of these, we had a speed one as well, we can throw that into the mix as well and put it into our equality. And so now we can get, we have a means of getting angles, speed, and wavelengths, and indexes of refraction, all in the same formula. So we can cut some of this out if we just need, we can get 2 of these 4, and we can find some very many useful values based on what we're given. And so these relationships are both for the ripple tank and for light. So here's just some interesting absolute indexes of refraction for just some various different types of materials and fluids and different types of mediums. And so notice we have for a vacuum 1.0000, and air is very close, but it still has some refraction, and so some interesting refractive indices. And so think of these as just more value of this has greater bending power. If a ray of light was to come from a medium into the second medium of any of these would bend much more down here, and up here these ones would bend not so much. So now we look at a problem. A 5 hertz, which is a unit of frequency, also can be treated as a unit of 1 over seconds in the math, which is known as a hertz. So a water wave traveling at 31 centimeters per second in deep water enters shallow water. The angle between the incident wavefront in the deep water and the boundary between the deep and shallow regions is 50 degrees. The speed of the wave in shallow water is 27 centimeters per second. So part A is we want to find the angle of refraction in the shallow water. And so we have one is deep, 2 is shallow, because we're entering shallow now, just for convention. And so we have V2 here, we have V1 here, and we have an angle. So the angle between the incident wavefront in the deep water and the boundary between the deep and shallow regions. So let's draw our scenario out. We have some waves going like the wave rate is like that. And our barrier something like that. And so we said this is deep going into shallow. And so we have a normal here, right? So at the point of contact on the barrier, on the boundary, perpendicular up. Try to draw this straight. This is the normal. And so now, what does our refracted wavelength look like? Well, we said when we're going from deep to shallow, or a slower medium, it's going to bend toward the normal. So let's, instead of going straight like that, it in fact bends like that towards the normal, right? And so these look similar, a little emphasized, but just so you get what it looks like. And so they'd be traveling the similar way. It's a little accented, but slight refraction. So, but as for the angle between the incident wavefront and the deep water and the boundary between the deep and shallow regions, that is going to be that angle is here between the deep water wavefront, or the waves of the incident wavefront, and the boundary. So that is our theta 1, and our theta 2, we want the angle of refraction, and that is here. If theta 1 is there, theta 2 is right there. So we want theta 2. We have theta 1, we have our speeds, and we have a frequency, and so we can apply our Snell's law and scratch out the ones we don't need. We don't need the frequency or the indices. We can use we want the angle, right? So we include the signs. We have both our speeds, so we just use those two. We bring over sine theta 1. When we have sine theta 2, we plug in our values, making sure that they're the same units. Centimeters a second, or it's okay here. Plug in our angle that we know, and when we do sine inverse of the result, whatever this is, we do sine inverse of that, and we're left with theta 2 equals 41.9 or 42 degrees. So we have our angle of refraction is 42 degrees using Snell's law. Next we have part B. Find the wavelength in shallow water. So shallow is our 2. We're looking for lambda 2. And so we have a frequency, and we know that in water tanks and light that the frequency doesn't change because it's determined by the wave machine. And so we have f2 equals f1 equals this, and so we're looking for lambda 2, and we have a frequency, and so this is sounding a lot like our v equals f lambda, our universal wave equation. And so we have this, and we want this, and we have our speed too. And so just rearrange. We do this for the shallow water, right? 2, frequency 2, which is the same. And so we rearrange, we bring F2 over, and we have both our values. And hertz here is per second. Remember, 1 over seconds, so that's okay. Centimeters is fine. And we come up with a wavelength of lambda 2 equals 5.54 centimeters, or 5.4 centimeters. And the wavelength, shallow water, we can say is 5.4 centimeters. Now let's look at a light example. So for a light ray traveling from glass to water, find the angle of refraction in water if the angle of incidence in glass is 30 degrees. So we're going glass into water. We're going to have some sort of refraction. And so we have our angle of incidence, which we know is going to be theta I, or in this case, since glass is the first medium, we can say theta 1, theta I, theta G for glass is 30 degrees. And so we want to find the angle of refraction in water. So let's say that is theta 2 or theta in water. So we have one angle and want to find one angle. So kind of getting the sense that we want to use Snell's law again. We're going to have a theta over a theta, and then we want to equate it to some sort of ratio we know. And so from the table we looked for at before, we have the ends for water and glass. And so that was a valid ratio that we can equate angles to. And so we just simply do Snell's law with the sine thetas and the ends. And we want to find, we said that our theta 1 is the theta of glass and the end of glass. And we said theta 2 is going to be our water one. So we have, where we see a 2, you make it the water, same here. And so we substitute our angle, we know 30, our mediums we found from our chart, and we have one unknown that we just need to solve for, so we bring it to the other side, and we get this, do sine inverse of this math, and we end up with our theta of water, or theta 2, of 34.3 degrees. And so we know our angle of refraction in water is 34.3 degrees. Next, for part B, we want to find the speed of light in water. So again, we're thinking we have a set of, we're going to want the speed ratio for Snell's law and equate it to the something we already know. So we have the indexes of refraction, N2 and N1. We found them from the last one, or from the table. They're readily available, so we are going to use that. And we have our V1 and V2. And so we said the 1 was we said it was our air, because for this problem we're going from air into water. So this would be our 1s, our 2s, and so our index of refraction is, we look up for air, it's almost 1. It looks like this is assuming that we're in a vacuum. We're assuming not normal air, so not technically NV, but we're going to go with this vacuum. Otherwise, we use 1.0029. You use the index for the material you're using. Waters is 1.33. And so we have our ends taken care of. We want to find V2 in water, so the 2s, so it's V2. Do we have V1? Well, in a vacuum, v1, the speed of light, is just the constant we know, as c equaling approximately 3 times 10 to the 8. And so we do technically know it. And so we take the proper ratios, our speed ratio and indexes, solve for v2 because we want the water, plug in our values, just making sure the units are matched and they're okay. And we come up with 2.26 times 10 to the 8 meters per second for 2, the speed of 2, which is water in our case here. So can we have reflection and refraction? Well, the answer is yes. So if you look at this diagram, this is a material called lucite. It's a plastic that is transparent, but it's a different medium. And so we have ray 1 as the incident ray, and it comes in, and when it hits the lucite, we do have some reflection, and we have one ray that is reflected, and the rest of it is refracted because it's entering from air or a vacuum, unclear from this picture, but that medium into a new medium, which is a lucite, and refracted. And so it's inside the lucite now, and when it comes and hits the mirror, it gets internally reflected. So we have ray 4, which is another reflection, and then it comes back out. And so in this, from 4 to 5, we have the medium switched. And so we have it coming from the lucite and into air or the vacuum, whichever one it is, and so it refracts once again. And so we have both reflection and refraction happening at the same system. So this double effect of both reflection and refraction is it occurs when it depends on the angle of incidence and around something called the critical angle, which is what determines what effect takes place. So if the angle of incidence is less than this critical angle, which is different for each type of medium, we end up with partial refraction and partial reflection, which is, as you see here, the diagram looks like this. A little bit of both, but weakly defined. You can see the reflection is small and the refraction is small and the reflection is also small. At the critical angle, we get very strongly defined both reflection and refraction. See how much more sharply it bends and how much more perpendicular the reflections are, and see how different this is compared to this, how much steeper it bends, how much more it bends towards or away from the normal. So that's at the critical angle. And then if you exceed that critical angle with your incidence, you can get something that's known as total internal reflection. And so, which is the reflection of light in an optically denser medium, which occurs when the angle of incidence in the denser medium is greater than a certain critical angle. So when this is reached, with these larger incident angles, there is no refraction at all, with all the wave energy being reflected instead. And so this behavior of light is referred to as total internal reflection. And that looks like this. It looks very neat. Notice that all the waves are being reflected and nothing's being refracted here. Nothing looks like that because of the incidence angle being greater than the critical angle. So remember those three cases involving this critical angle. You have partial refraction, partial reflection. At the critical angle, you have this nice strongly defined of both. And when you exceed, you get total internal reflection. And that's the end of the lesson for today.